All right, hello everyone and welcome back to Physical Geology 1403. Let me just make sure my microphones are both working here. Yes, they are. Fantastic. Turn off these lights at the front. I am not joined by my snake today. Diablo ate yesterday. Typically I'll feed him on Saturdays and he'll be good to be handled and come out to play by Tuesdays, but my rat guy was unable to fill any orders this weekend because his entire street is being dug up by a city water department because it started to flood and they're trying to find the breakage and all that. So I had to go get a rat from him yesterday, and so Diablo is still digesting that. So we'll just let him be for today. Probably on Thursday. Huh? Running? I don't think Diablo's much into running.
No, I meant like your rat guy's pipes.
Oh, I see. Because the pipes broke, that goes along with this. I'm there with you. Nice. Okay. First order of business. The first exam, exam 1, is done. You are done with module 1. That's not to say we will not continue to talk more about, love your shirt by the way, NSYNC, great band. That's not to say we will not continue to talk about the material that we learned in module 1. We're going to keep coming back to that. But the class builds on itself, okay? The things we discuss in module 2 rely upon you remembering, being familiar with what we learned about in module 1, okay? So you did great. Thank you for taking the exam. If you have not taken the exam yet, as you are watching this, right now you should be going, oh, crap. Take it, okay? Take the exam before you watch any more of this, okay? Let's see what else. Module 2 is 4 lectures long, so you're going to get module 2 today, the next time we meet, and then the next 2, so next week, and then the week following. So in 5 lecture days from now will be exam 2, okay? And then we'll go up to that point. Any questions about that? Any questions about anything at all?
Are the exams getting easier?
The exams will maintain the same standard as far as difficulty. I try and keep them at about the same level. Bear in mind that the final will be cumulative. So if you think that makes it harder, then perhaps it is. It will cover all 3 modules. So you may need to refamiliarize yourself with the stuff from module 1 more than anything else, because they will have been the longest since we talked about that. But let's cross that bridge when we come to it. You'll be fine. I'm glad that y'all are feeling a lot more confident after this exam. Okay. Any other questions? Anyone feel that earthquake yesterday? It was in West Odessa.
I didn't feel it then.
No? It was a 5.1. Not too big on, as far as, I don't know, if you're familiar with the scale of earthquakes, which we will talk about later in this semester. It was a 5.1, so enough to shake and rattle a few things. If you were paying attention, you probably noticed. If you weren't paying attention, you probably dismissed it as a semi-truck driving by or something like that. Huh? 7:45.
Yeah, I didn't feel it.
Okay. Sometimes when I'm up here and it happens, I'll feel it. If the higher up you are, the more glass your building has, the easier it is typically. When we had that 5.3 last year, it kind of felt like a car slammed into the building. It was like, what was that? Right? And then we realized what it was. Okay, well, if you ever are just kind of standing around and things just kind of shake a little bit, it's probably an earthquake. Why do we have earthquakes here? We will learn about that later this semester. Okay. Shall we begin? Hi, Sebastian.
Morning.
How you doing?
I'm good.
Great. Shall we? Okay. Today we're talking about mass wasting and running water and groundwater. Okay? It's kind of lumping a few things together, mostly to just save time. I only meet with you 13 times throughout the semester, so I need to make sure that I can consolidate subjects as often as possible. So we're going to start off with a conversation about mass wasting. Can anyone remind me what mass wasting is?
Is it like landfills or dumping things into the ocean?
No, it is not landfills or dumping in the ocean. Thank you, though. What else?
Is it about the soil
What about soil?
going to the ocean?
Not about soil going into the ocean. Although mass wasting is a form of erosion. We learned about mass wasting a little bit when we discussed weathering and erosion. Mass wasting is when stuff like rocks or other debris erode under the influence of gravity. Water's not pushing it, wind isn't driving it, only gravity is giving it the necessary energy. So before we can start diving in deeper into mass wasting, we need to understand gravity a little bit better. All right? Who can explain gravity to me?
Force that makes everything go down.
A force that makes everything go around?
Down.
Down. We'll discuss exactly what down means in a minute. But let's just sum it up in the most basic Isaac Newton way possible. Stuff falls. Right? Fair enough. That's gravity. Why is stuff falling? Well, stuff falls because gravity is pulling objects. Where is it pulling objects? To the center of mass itself. Gravity is a force that we are still only just now learning more about. Every day we learn a little bit more about it, mostly by observing things in space. I'll talk more about that in a moment. But gravity is a force exerted by all objects that have mass. All objects. An atom has a certain amount of gravity to it. You have a certain gravity to you. I have gravity. This remote has gravity. This pen has gravity. Gravity is the force that causes one object to orbit another, to stay in its proximity. That's why the Earth orbits the sun. That's why our sun has a lot of planets orbiting itself, right? And why our star system itself orbits around our galaxy. Why our galaxy orbits around in a supercluster of galaxies, and why that supercluster of galaxies orbits around, we presume, something in the middle of the universe. Though what that is, still up for debate. So then tell me, why is this pen not orbiting me right now? I have more mass than this pen, correct? Yes. Why is this pen not orbiting me? If smaller objects orbit around the gravity due to the gravity of larger objects, why is this pen not orbiting me? Okay. Huh? There's something else bigger. What is it? The Earth. The pen isn't orbiting me. It's drawn to something else. It's drawn to the biggest, toughest thing around, gravity-wise. Our planet. Okay? If I were in deep space, far, 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 far away from any other gravitational body, it is conceivably possible that, yes, this pen might orbit me or stay in my proximity. It may not actually orbit me because that takes a certain process. It needs to have had a certain amount of momentum to begin with before, gravity kind of forced it into a certain stable orbit, but that's not math we're going to go into. It might stay in my proximity, though, because I'm the largest gravitational body nearby. Okay? I am exerting more influence on this than it is on me, just like we are exerting more influence on the moon than the moon is on us. Okay. So, Angel mentioned a word earlier. Down. What does down mean?
No, no.
Not up. Okay, well, answering, giving me a definition of a thing by telling me the opposite. I mean, that's one way to do it, I guess. All right. Well, here we have Earth. Nice and round and purple today. Okay. Here is Zara. Hello. She's right here in Odessa, Texas. Angel took a little trip to China. He's standing over there. Okay? Are you enjoying yourself in China? It's been a good trip. You had some good food?
Yeah,
Great.
nice
Okay.
people.
Yeah? Okay, so you just bought yourself a nice, yummy noodle dish. Okay? I don't know what it is. There are so many different kinds, but let's just say it's a delicious noodle dish, okay? And you're walking on the street, you have eyes only for your noodle dish because it's lunchtime and you're starving, right? It's not hard to understand right now. And you trip on something, you drop your noodle dish, and it falls what direction? Down. It falls down for you. Now, if Zara, what are you eating right now? What are you eating right now? Funyuns. If Zara were to dump out her bag of Funyuns right now, what direction would it fall? It would fall that way, right? Because that's the direction your noodles fell.
Yeah,
That'd be funny.
it would obviously fly.
Isn't that how it works?
Stick it to the ceiling.
Right, it would just go up into space. No. What direction do they fall? Down. Okay, so down for Zara and down for Angel are totally different vectors depending on where you are on the planet. Right? If Cade's hanging out over here somewhere in the Pacific Ocean, down for him is that way. Right? If Emily's hanging out somewhere over here, in a location that I can't think about at the moment, I can't think about what's on the outside, probably somewhere in Europe. I'd have to think about that. But somewhere over there on the opposite side from Cade, vector is that way for down. We live on a sphere. And all downs, no matter where you are in a sphere, point where? The center of what? Mass. When you hear the term center of mass, normally it's someone referring to the fact, oh, I have a very low center of mass. You know, that's trying to explain why they're so clumsy, why they trip all the time. I have a low center of mass. I can't help it. Excuses. No. In a sphere, though, the center of mass is always, guess what? The center. Is that always, however, the center of gravity? Ooh, this is a tricky question. This is mean of me. For now, for as far as Earth is concerned, yes, our center of gravity is the middle, the very center of our planet. However, well, not our moon. I can give you an example of a celestial body where the center of gravity is not at the center of its planet. And I think I actually mentioned it to you in a previous lecture. Pluto. Yeah, you remember we talked about this? It didn't mean anything to you at the time, but now we're talking about it, okay? Pluto and its moon are so close in mass. I think the moon of Pluto is maybe like 30% the mass of Pluto itself. They're so close in mass that they are drawn to each other such that the center of gravity for Pluto is actually in space between itself and its own moon. That's not the case with our moon. Our moon is about, I think it's 1/50th the size of our planet. So it doesn't exert that kind of influence. It does have gravitational influence, which we will talk about at a later time. Just as examples, tides are caused by the moon, right? It's gravity. And funnily enough, the mass of water, we have so much water on the surface of our planet that is drawn to the moon's gravity that the gravity of all that water also pulls on the moon a little bit. So there's a little bit of back and forth between our planet and the moon there. Yeah.
Isn't the moon still being like flung away from us?
The moon is moving away from Earth ever so slowly. Yeah. Its momentum is just slightly greater than its gravitational pull to the Earth. And so it's not very much, like an inch or two a year sort of stuff, right? But yeah, if you had been standing on the Earth 4 billion years ago, the moon would have been much, much larger in the sky. And now, as far away as it is, in another 100 million, 200 million, 300 million years, it'll be even further. Now, it's not going to completely fly away, we don't think. If the math is right, it is kind of going to slow down that rate and eventually find parity. It's going to end up a certain distance and probably stay there. We don't really think it's going to just zip off into space. Again, that's all we can do is math, right, for that. Anyways, let's come back to this concept, though. Down is relative depending on where on the sphere you are. And so, but wherever you are, gravity is going to be pulling you there, okay? Now, why is this pen not falling down right now? It's just sitting there. Why aren't you falling? Why isn't it falling?
The table is obstructing.
It's what?
Is it because the table is obstructing?
It's on a surface. It's being supported, right? What about if it's not being supported? Or what about if I remove its support? It falls down towards the center of the planet, right? That's mass wasting. Something, in this case a pen, but for the rest of our conversation today, it'll relate to rocks, okay? Falling under the influence of gravity. Now, for something to all of a sudden just fall under the influence of gravity, something has to have been removed that was there previously. Some kind of support, okay? So, these rocks, there's no tractor there pushing them. There's no wind that made them fall. There's obviously no running water here. What happened? They fell because whatever support they had no longer was stronger than the influence of gravity upon them. Gravity is constant. It's not like all of a sudden gravity increased right there, right? What did happen? The support wore away, weakened, weathering, erosion, dynamic processes on Earth's surface removed that support to the point where all of a sudden, at some moment, gravity won. That's mass wasting. Now, a lot of this has to do with something called the angle of repose. The angle of repose, I recommend writing this down, is the maximum angle at which an object can be at rest without falling under the influence of gravity. I'll repeat that. The angle of repose is the maximum angle at which an object can be at rest without falling under the influence of gravity. Someone explain that to me.
Like if it's like this, like the angle like this, it's not gonna fall. You put it like this, it falls.
You said this like 5 times.
Yeah, like this.
Okay. What, instead of saying this, describe what you're doing to me. Let's use some technical wordage here. We're in a science class.
Let's say you have like this notebook,
Okay, you have given me a surface,
And then this pen.
an object. Okay, a pencil. It is slipping off of your surface
Yeah. Because of the angle.
because of the angle. So is there an angle at which it will not slip off your surface?
Like this.
Okay, where's the angle at which it will slip? There it is, you found it. The pen slipped off of his notebook once he tilted the notebook to reach a certain angle. That is the angle of repose. I'm about to do a demonstration just like that. Here I have a wooden board. A surface. This is the surface, okay? Just a normal wooden board. It's like I'm about to do a magic trick, right? There's nothing here, just a normal wooden board. Yes, I'm positive. Okay. Here I have one Lego, a brick, 4-peg brick, square shaped, right? I place it on my surface. And as long as the surface is flat, the Lego stays there. But if I start to tilt this board, what's going to happen? Eventually, I'm going to reach an angle at which this Lego starts to move. There it is. Bye, Lego. Okay, right there. That is the angle of repose for that object. Now let's try with a different object. A marble, perhaps. Holding my board still, and then creating an angle. Do you think I'm going to have a larger angle of repose or smaller angle of repose? I barely make any angle at all before it's gone. That is the angle of repose for this object. So what then can we construe? What hypothesis can we form about the angle of repose? What is it dependent on? Objects have their own angle of repose based on what?
Shape and size.
Shape, size, material, composition. Yes, these are the things that dictate an angle of repose. This brick of Lego is made out of plastic. Perhaps the friction coefficient, y'all have taken physics, right? You're familiar with friction coefficients. I can't tell you what it is between this object and that object, but it has one. The friction coefficient between this plastic and this wood may be greater than that between this glass and this wood. But also, what about the shape? Flat surface, sphere. What's the big difference between the way that these two shapes interact with this surface? Independent of whatever it's made out of, or even its size. What's the big difference between these two shapes for its interaction with this surface?
It has like something to rest.
It has a flat bottom, which means what? More friction because of greater, surface area. How much of this marble surface at any given time is in contact with that board? Very little. If I had a Lego made out of glass, I guarantee that Lego made out of glass would have a larger angle of repose, not because it's made out of glass, but because it is not a sphere. That is why the shape has a lot to do with your angle of repose, the shape of your objects. More surface area equals greater angle of repose. Do we understand angle of repose? Any questions about that? No? Great. How are we doing? Awesome. What are you eating? Lay's? What flavor? Lime. Nice. Feeling zesty this morning, huh? Okay. So, you remember learning about cinder cone volcanoes. right? We discussed these a few weeks ago. Cinder cone volcanoes are the smaller types, right? The ones that have very steep sides. Why are they so steep? Even though they are not very, they don't live very long. How do they get so tall and steep? Because they are made of scoria. This stuff, jagged and chunky, and feel this surface. It's like sandpaper on my skin. There's a lot of surface area on scoria that grabs and holds on and sticks and has friction with a lot of other surfaces on a lot of other pieces of scoria. And so cinder cones made out of this stuff get big, or not big, but tall and have very steep sides quickly because less of this is likely to roll away because the angle of repose is so high. Okay? If your slope is made out of material that will enable a high angle of repose, you get a steeper slope. So if I have, say, fine sand, nice, well-rounded, small sizes, right? I might have a 35-degree angle of repose. What does that mean? If I dump more sand on this pile, then sand is gonna fall off of that slope until the angle of repose is reached for that material. Okay, about 35 degrees, let's say, just as an example. Okay, then if I increase the size and maybe also the angularity of my sand, it's not quite as spherical. I might have a 40-degree slope. Now let's say I'm talking about pebbles, and they're not weathered at all. They're angular, they're blocky, right? They've got those lots of surface areas that grab and hold on to each other. Perhaps that'll have a 45-degree angle of repose. So, mass wasting, that downhill movement driven by gravity. Water may be present, but is not the driving force. Okay? So if you look at this slope and you watch these rocks falling, this probably is a stream bed, but you cannot see any water. None of this is being driven by water. These rocks are free falling. That's pure gravity. And by the way, watch when this rock reaches the bottom. Look at all these even bigger rocks that fell down prior to that some time ago, right? Water didn't push those. Those all fell under the influence of gravity. Now, this often leads to material getting transported away by water or wind or whatever the case may be. But mass wasting is its own subcategory, let's say. So let's take what we learned about angles of repose and apply it to a real-world scenario. Y'all ever been to the Grand Canyon? Just kidding? Okay. Well, the Grand Canyon looks like this. What do you notice about these slopes? Are they all the same? No, we've got steep and gentle, and then gentle and steep and gentle and steep. The Grand Canyon does this in cross-section. Why is it doing that? Why is the Grand Canyon not just, why aren't its sides just like that? Explain this to me.
Maybe the top, like going down from, they go down, it creates like a bigger, and then they go down again, like bigger.
Not sure what you're trying to say. Can you add more words in there?
You see how the top is like more flat, like less, like less big than the bottom?
Less steep?
I don't know what does like
steep is like your angle. This is more steep, this is less steep, right?
Aaron will tell me
You're gonna help him out, Aaron?
yeah.
I'll get you in a second, Cade.
The fact it's going down out of the angle means gravity is pulling it down.
Gravity is pulling things down. This is true. I'm looking for an explanation for why there are so many different angles here. Yeah. What do we have here? Limestone, sandstone, shale, sandstone, shale, limestone, shale, sandstone, shale, and then schist. Where'd that schist come from? Well, that's a totally different story. Okay, that is extremely old schist. There's something that exists right here called the Great Unconformity. It's about 2 billion years of missing time right there. It was all eroded away. It was all weathered and eroded away before the rest of the stuff was deposited on top. That's a whole fascinating story for a different class. Regardless, you've got all these different types of materials, and each material is unique. Each layer of rock, perhaps the sandstones, have different grain sizes, sphericities, cementation quality. Perhaps the limestone, one layer is fossiliferous, may not necessarily be very tough. Perhaps another layer is micrite, very tightly bonded calcite crystals. Limestone is softer than sandstone, but is tightly compacted, right? Shale, not very tightly compacted, falls apart relatively easily. Notice our shale layers tend to have shallower angles, and our limestone and sandstones tend to have steeper angles. What are these angles, by the way? The angles of repose, the natural angles at which those materials bind. Stuff falls off, material falls off of these layers of rock until those angles of repose are reached. So then one begs the question, why, after the angle of repose is reached, does stuff continue to fall off? We have reached the ideal angle of repose for each of these layers of rock. Why does sediment continue to fall down slope into the Colorado River? Why doesn't everything just kind of stop there? Okay, we found our angle of repose. We're gonna stay here. Gravity's not, gravity's always pulling it, but gravity isn't driving it downhill at the moment because it's at the angle of repose. Dynamic Earth. Earth is dynamic. We've got that wind, we've got that water, we've got earthquakes, we've got all these things. We've got little kids on the side of the Grand Canyon kicking rocks downhill, right? We got all sorts of things on our planet that are going to shake it up, okay? In the case of earthquakes, literally, right? There is always going to be something that causes those angles of repose to get messed up. You dump a bunch of rain on a slope, and guess what? All of a sudden, you lose a bunch of the friction holding your grains of sand together. So while a dry sand may have an angle of repose of 35 degrees, a wet sand, like a really soaking wet sand, won't. Have any of you built a sandcastle before? What happens when can you build a sandcastle with dry sand? No. What do you do to the sand first? You get it a little wet. It makes a bonding effect due to the cohesion qualities of water, which we will discuss next lecture, okay? But what happens if you add too much water to it? What do you get? You get a saggy, wet puddle of sand. You can't make a castle out of that either, can you? So if you add too much water, the friction between your grains falls apart, and where your dry sand may have had an angle of repose of 35%, your soaking wet sand might have an angle of repose of 10. So you make a whole bunch of rainfall, all of a sudden your stable slope becomes unstable because its angle of repose is less. Stuff's going to fall off that slope as a consequence. Mass wasting continues. Make sense? This is what we call landslides. A landslide occurs because the angle of repose has been surpassed for one reason or another. There are several examples that y'all should look up in your own time when you have an opportunity. I've given a few lists here. There have been pretty infamous landslides in Panabaj, Kashmir, and Philippines. Okay, you can look those up. Just look up those names with landslide in Google, and they will come up. You'll see devastation on this scale. Okay, right? But what can happen to cause these? Rainfall, very common. Landslides are often caused by earthquakes as well. Well, what does an earthquake do? Right? An earthquake shakes the ground up and down. Also, there's some side-to-side motion. We'll learn about both of that when we talk about earthquakes in a few weeks. Okay? Do you think that up and down and side-to-side motion is very friendly to a stable angle of repose? No. My angle of repose is doing this. No longer stable, no longer reposey, right? It's not a word, but you get what I'm saying, right? It is no longer at repose, okay? So, also, unfortunately, we can cause these things to happen as well. We often will divert waterways, the natural course of rivers. We'll make canals. We will build dams and increase the size of reservoirs, okay? And so we'll affect running water in some ways, and those can work to remove the support of nearby structures, which ultimately will fall due to mass wasting, okay? Industrialization. Do you know how much cities weigh? Imagine all the steel and the glass and concrete, just the concrete alone, and asphalt and the plumbing that a city weighs. Billions and billions of tons for the larger cities, I would wager. That's a lot of weight. And that's going to have an impact on whatever slope that city is built on. Okay? Also, deforestation. You remove the plants, what's going to happen to your soils? Yeah, there's not a whole lot holding them together anymore, and they are more likely to fall. Maybe washed away, maybe just tumble down slope, depending on the angle, right? Angle of repose is all well and good, but if there's a bunch of plants and trees growing on that slope, it's going to hold that soil there regardless of the angle. But you remove those trees, all of a sudden, nothing's holding it there. Okay? So we can cause this to happen ourselves. Let me give you a few examples here. In La Conchita, California, 2005, there was heavy rainfall outside this community. This slope, made mostly of clay and clay and sand, got saturated. This is a part of the country that does not normally receive heavy rainfall. And so this angle was the angle of repose. Look how thickly forested it is, right? A lot of those plants were probably holding it in place, lending to the fact that it could be a steep angle of repose. But what happens if you saturate that rock, you saturate that soil? All of a sudden, what happens to our friction? Plummets. And this hillside just collapsed down into this neighborhood. Came down so fast, it pulverized houses. Okay? I'll give you another example. Do you remember when I was telling you about volcanoes? And I told you about that town I lived in next to Mount Rainier, Ording? Well, one weekend, and this is not weird for Seattle, by the way. They only get like 40 days of sun a year. Otherwise, it's usually raining or at least cloudy, okay? But we got like 7 days straight of heavy rain out there. It was a lot, even for Seattle. And I remember this vividly because I was just kind of walking around doing my routes, and all of a sudden, I hear sirens, and I hear people yelling, jumping in their cars, and all of a sudden, roads are just packed. Everyone's leaving town, like every first responder, a bunch of citizens. They're heading down the road. I'm like, what the heck happened? Well, in the next town over, Oso. This is Oso right here. This is pretty much the whole community. There are a few other things out here and a few more other things down here, but this is the main community. Everywhere there's a red circle, that's a home or a business, okay? This is the next town over. This hillside became saturated with rain and collapsed into the river, which caused all the water in that river to basically tsunami out over here. And then this hillside, like all of the sediment kind of bulldozed its way through there. And this is what Oso looks like now. That's what happened that day. So pretty much the entire community was gone, killed 43 people. This is the most deadliest landslide in recorded US history. Not in the world, there have been far, far worse around the world, but in the US, since we've been keeping track, this is the deadliest landslide. And I mean, you know, in these little communities out there, everyone knows everyone. And so people in my town, I wasn't from there, so I didn't know anyone in Oso, but a lot of the people that grew up in Ording were very familiar with the people in Oso, and that's why like my town emptied to go see what they could do to help the people in Oso. It's quite the tragedy. Okay, so what can we do about this? Well, unfortunately, options for stopping it are limited. Okay, prevention is the best solution. Trying to pay attention to where they might happen, prevent people from living in those places at all, or at least give them the option. Say, hey, just so you know, this is a danger here. Let them make the choice from a place of being informed. Okay, or there are some measures we can take to try and prevent that. Retention walls aren't really great because stopping something like this, a force of nature like that, it's extremely difficult. And so the best way that we can do is to just the best thing we can do is try and make sure that we understand when and where and why they are going to happen. Okay? So we can make maps like this. Okay? You can use what's called a geographic information system. Okay? GIS software. You guys ever heard of GIS? No? You probably will at some point in your careers. A lot of businesses use them these days. Okay, but for this particular example, I can take a map of the United States and then I can get a spreadsheet of data. Let's say I went to the US Geological Survey and said, hey, I would like an elevation map of the United States and I want the data sheet for it and I want to overlay it on top of this. So I can get all of the mountain ranges that the US Geological Survey has recorded in the US, and I can use that data and I can overlay it on this map. Okay, cool. Now I want, maybe I go to the National Oceanographic and Aerospace Administration, NOAA, and I say, hey, I would like your data on the rainfall in the United States. And I can take that information and I can overlay it on top of this map of the United States. Okay, maybe I can go to, this might actually take me back to the USGS. I would like to know where all the running water is. Where are the rivers? Where are my streams? All of that, okay? And I can overlay that here. And then as I have all these maps overlaid, anywhere that those three things overlap each other, I can color code. And then based upon how much the overlap is, how high, how steep my mountains are, how much water is running through that river, how much rainfall I get per year, I can then color code those overlaying areas, and I can say everywhere that is red has a very high potential for landslides. Everywhere that's orange has high potential, green is moderate, and colorless has low. Yes?
Eastern side of that, is that where the big red car, is that where the Appalachian Mountain was?
Yes, this is the Appalachian Mountain Range right there. Yep.
Why it's so high?
It rains quite a bit. There's a mountain range there. It's old rock. And there's also a lot of mining that happens out there. And there are rivers that run through there in the valleys. There's a lot that goes on over there, okay? As you can see, we are in quite a bit of danger in our part of the world.
Yeah, it's very dangerous.
Yes, extremely dangerous. Landslides are something that we have the potential of living with every day, right?
Yeah, don't you see the mountain?
You live in fear?
That does, you know what makes
Rightly so. Rightly so. Now, let's talk about that for a minute. Why don't we have any danger of landslides here? Yes?
Flat area, like desert.
It's flat. We have no mountains. Okay, cool, cool. So that's like, let's take that off. What about heavy rainfall? Sometimes, but yeah, it doesn't happen often. When it does, boy, do we flood. But it's not because of landslides. It's not snow. We don't have soil that's conducive to let it soaking in, right? As we learned in a previous lecture, right? So it's like, okay, what about moving water?
We don't have any rivers or anything around here.
Where's the nearest river?
Probably miles away.
It's miles away. We don't have anything large enough nearby to be of concern. The largest river that we have nearby is the Rio Grande. That's the largest river that's anywhere nearby. And that's all the way over there. Right? And it's dry half the year anyway these days, right? You guys ever been rafting down the Rio Grande? It's like gambling. It's like you could show up with your buddies and your rafts. You could driven 4.5 hours to get there, and the water's this deep. Yeah, so, all right, so that explains it. We don't have a lot of potential. We have other potential disasters that could happen here, but not a landslide. I can make a map like this to chart other potential disasters, and often people do. City disaster management departments make maps like this so that they can give city officials, they can give county officials, they can give state officials breakdowns. Hey, this is the potential risk based upon the most recent data that we've acquired. Okay, well, if there is a risk, let's make a disaster plan. Okay, so you better believe towns out here have landslide disaster plans. Out here, it's probably more along the lines of flood or drought or famine, right? Or pandemic, things like that. Disasters don't always have to be the my house got bulldozed by a rock kind, right? All right. So now let's talk about how we classify these landslides. How do we give them these names and tell them apart from each other? Well, the word landslide itself is an example. The first thing that we do, the first part of the name has to do with the material involved. If it is unconsolidated material, that includes debris and mud. So if it's just loose, unconsolidated stuff, it'll either start with debris or mud. If it's just a solid layer of rock moving, we will call it, or a whole bunch of bedrock, we call it, it starts with rock. For example, taking that landslide name, I could call it a debris slide or a mud slide. You ever heard of mudslide before? Okay. Versus a rock slide. Mudslide, mud. Rock slide, rock. Okay, pretty easy to follow. The next part of that word, that slide part I've been using, has to do with the motion. Now, slide is one option, but fall. If it's a fall, it's just pure mass wasting effect. It is falling. That was a pen fall, right? It didn't slide off of anything. It straight up fell off the surface, okay? A slide is when it is traveling down a slope, okay? And the type of slide has to do with the motion. So there are two types of slide, rotational and translational. Let's talk about translational first. It's the easiest to comprehend. In a translational slope, I have one layer of something sliding over another layer of something else. This could be a layer of sandstone sliding over a layer of shale. Or the opposite, shale sliding over a layer of sandstone, depending on the situation. Okay? But it's one layer of something on top of another layer of something else sliding over a linear surface. In a rotational landslide, this usually has more to do with that unconsolidated debris that we talked about earlier, okay? Normally what will happen is this becomes saturated, it becomes soaked, your friction is gone. And so you start getting some downhill movement. Well, because this is loose material, instead of sliding straight down, it tends to compact down straight down. In the straight direction until finally it's so compacted, it's compacted so much down here that it has no choice but to kind of scoop itself out back onto the surface and travel downhill. And so you don't get a just motion, you get a motion like that. That is a rotational slide. And then depending on the speed, we may refine that name even further down based upon its rate of movement, but We won't really go into that in this class. What you really need to know about is the material and the motion. That's what dictates it. So the term landslide is just a general term. Okay? You can have mudslide, debris fall, rock slide, rock fall. Again, based upon the material and the motion involved. Great. Let me give you some examples. Slumps. This is a type of rotational slide. So again, you've got downward movement straight down until this is so compacted that your material has no choice but to kind of push back out onto this surface right here. Okay? So you get this rotation outward back onto the surface. This is a real life example of that. Now, can anyone looking at this picture tell me what probably happened here? Notice how we've got this sort of step-like pattern on top, like we have in this picture here, in this example. Look what happened to this road. It's been fractured into a bunch of pieces. They probably didn't know this was going to happen when they built that road, did they? What do you think happened here? Look at this picture and interpret to me what most likely happened.
River
River where?
in the bottom.
Hey, look at that. There's water down here. Now, is it a river or is it a beach? Don't know. Not enough context. But keep going. What is it doing?
Going against the rock, taking away the material.
It's removing support. Until finally, gravity overwhelmed its ability to support itself, causing this rotational slide. Good. This is an example of a rock slide. Now, have any of you ever driven down the highway and seen, Jocelyn's already nodding, yeah, I've driven down a highway, right? Good. Okay. And seen where they cut through the rock to make that highway, but instead of going against the layers of rock, they went with them. So like your highway is right here, and there's just a flat layer of rock there. Dumb move, right? Why? Yeah. What happens if this layer detaches from the layer under it? Your highway's a goner. And so is anyone that was on that highway at the time, right? Rather than construct a highway parallel to the slopes that have these layers of rock pointing towards that highway so that this happens, it's always a good idea to construct your highway. Where's my engineers? Right here, okay? Always a good idea to construct your highway so that when you are blasting a path for your highway, you make your slope perpendicular to those layers of rock. Why? Because you're not going to get a translational slide off of these layers in that direction. You will this way, though. And that's a big part of the reason why, like, so many highways in California, for example, constantly have rock falling on them. Because the engineers didn't consult a geologist. Surprising number of problems would be solved if that happened.
Who needs that geology?
Huh?
Who needs that geology?
Who needs to take geology? Said the guy halfway through the course. Okay. Now, in a larger scale example of this happening, in Gravant, Wyoming, okay, which is spelled like that, Grosventree, okay, T-R-E, I think I said 2 E's there. Gravant, there was a river running through this valley, okay, but then after some heavy rainfall, this sandstone, this is all sandstone right here, okay, this layer of sandstone became saturated with water. Remember, sandstone, very porous. It can hold a lot of water, a lot of liquids, right? It can hold oil. It can hold water. In this case, it got filled with water. What's underneath of it? Clay. That clay not letting the water through. That water cannot continue down through the clay So it built up in that sandstone, and eventually the saturated sandstone slipped over the surface of this clay bed. And what was it, like 15 something? I think it was like, no, maybe, I think it was like 8 kilometer strip. Yeah, that's a kilometer right there. So like 1, 2, 3, 4, maybe 4.5 kilometers of sandstone bed. Downhill, translational slide into the valley, cut off that river, and now there's a lake there. I've been here. Like the scar left on that hillside, I can't even imagine how loud it must have been to be standing there in that valley while all those millions of tons of rock just slid downhill into the valley. Must have been deafening. It's truly impressive to see. But that's an example of a rock slide. Okay, debris flows. Debris flow is a whole bunch of unconsolidated material that is usually accompanied by water. Okay, water is not the driving force, gravity is, but there is water present, right? An example of this, lahars. Do you remember lahars? What's a lahar?
Water, steam.
Not steam. When did we learn about lahars?
Week 2.
Yes, in week 2. Someone, yes, it's perfectly appropriate to go through your notes. Tell me when you find what a lahar is.
It's,
Is it a type of volcano?
Mm-mm. No, it is associated with volcanoes, but it is not a type of volcano.
oh, okay. Yeah, so ice from the tops of mountains, I guess, melted and then create a mud flow.
Yes, so the glaciers and snow that reside on volcanoes melt as a result of the volcanoes heating up during its preparation to erupt, right? And as a result of all of that melted ice water, it flows downhill under the influence of gravity, right? Ripping up everything in its path until you end up with a debris flow, a lahar, okay? Now, that is one example. You can have this process without needing the lahar, okay? You don't necessarily need to have a volcano erupting, melting glaciers, and all of that, okay? Really, just anytime you've got a whole bunch of debris and water flowing downhill, it's a debris flow. And then when it reaches the bottom, a flat area, all the energy of that transport is lost because all of a sudden the slope is gone, right? Angle of repose has been reached or surpassed. And so all the material in that water just kind of drops out. And that makes what we call an alluvial fan. This fan shape, that is an alluvial fan. You usually find these wherever rivers reach or streams reach the bottom of mountain ranges, wherever floods empty out. Earth flows. An earth flow is when you have, in a very humid area, your soil, your topsoil, kind of gradually just moves downhill because it's got enough water in it and there's enough of a slope that it's just kind of slowly migrating downhill, and it's very slow. Okay? Just all of this kind of gradually making its way downhill, that probably took 20 years. Okay? And then there are creeps. Ladies, you already know this. Creeps are everywhere.
Wow.
Yeah. No, but really, they are. These are literally everywhere. And after I tell you about them, you're going to see them everywhere. Okay? A creep is what happens when your soil is gradually moving downhill, not like an earth flow because it was so humid that it got saturated, but in a freeze-thaw cycle. So what happens if I have soil on a very slight slope and then winter comes and the water in that soil freezes? What direction does it freeze in? Those crystals of ice are going to grow in what direction? Perpendicular. Why am I using brown? That does not show up very well. Perpendicular to the angle of the slope, right? So if my slope is at, say, an 8% incline, okay, or decline, then I'm going to make an angle at 90 degrees to that with my ice crystals in my soil. And so my soil is kind of going to get picked up by all the ice crystals forming. And then when it thaws, what direction is it going to go? Straight down. Because gravity's pulling it down. As the ice crystals melt, it's going to move straight down. And so year after year, I'm going to have movement downhill like so. Freeze thaw, freeze thaw, freeze thaw, freeze thaw, freeze thaw. And even though it is very slow, it is powerful. All your soil rising with those ice crystals and then falling with gravity, and rising with the ice crystals and falling with gravity. Doesn't move very much, but it's all moving at the same time. And so it tends to pick up and move whatever's on top of it. Have you ever been driving next to someone's fence and you saw their fence did this weird woo thing for no reason? There's probably a creep under that fence, picking it up and moving it along with the soil. Have you ever seen a sidewalk do that, where it deviates for no apparent reason? Or maybe the asphalt somewhere on your street has gotten warped, and you can tell where the grain of your asphalt kind of moves off in that direction. Maybe it's starting to crack along that area. That's a creep. How about a curb? Let's look at this curb. This picture was taken in 1971. Okay? There is one part of the curb. Look, it's already separated by an inch and a half, maybe 2 inches. 3 years later, 1974, right? Probably a good 3.5, maybe even 4 inches there, depending on, I guess, how much that pencil was used. Using a pencil for scale is such a bad idea. I have no idea how much of that pencil you used before you put it there. Right? Give me something of a standard size, please. But regardless, you understand, it's bigger. The distance is greater. 1993, the year I was born. Check that out. The two curbs aren't even touching each other anymore. There's about an inch between them. And now 2005, there's about 2.5 inches between them. Why are the two halves of this curb separating from each other? Because there is a creep that is causing this part of this area to move gradually this way and probably downhill some direction that way, okay? But it's moving that way. And this is a physical expression we can see from the infrastructure built on the surface. That is a creep. And then lastly, solufluction. That's a fun word. This basically happens out where you've got tundra, permafrost. Okay? If you're familiar with permafrost, permafrost is basically a portion of the soil that is permanently frozen. Only the top few inches of soil ever thaw during the year. Like, I'm talking up North Alaska, northern Canada, Siberia, right? Permafrost. And so because only the top few inches of soil ever thaw, while they are thawed, they slowly kind of migrate downhill on top of the surface of frozen soil beneath them. And so you kind of get, when you're, let's say you're in a helicopter looking down at a permafrost area, you kind of make these sort of wavy effects. These waves are actually just kind of Waves of soil slowly making their way downhill on top of the permanently frozen soil beneath them. That is soluflection. All right, any questions about mass wasting?
Does avalanche like count like?
Ooh, does an avalanche count? Tell me why would an avalanche count? What made you ask if an avalanche counts?
It's more like sun or something, you know, like it's not caused by earthquakes, you know, like
It is falling under the influence of gravity. Is an avalanche made out of rock? Isn't it? What is an avalanche made out of?
snow,
Snow? Ice? What is ice?
fresh water.
Frozen water. But, huh? It's an oxide mineral. Ice is an oxide mineral. Didn't we learn about that? Any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. Does ice not fit in that category? It fits all 5 of those requirements to be a mineral. Ice is a mineral. Ergo, avalanches are mass wasting. Excellent observation. Okay. Shall we move on? All right. Running water. Better go catch it. You guys have heard that dumb joke before, right? Is your refrigerator running? Better go catch it.
Now it's broken because of that.
It's broken because of that. You're just going to go home and break your refrigerator just to spite my joke. Fair enough. Yeah, it's probably deserved. Okay. Remember, Earth is characterized by a bunch of spheres: the atmosphere, the hydrosphere, the biosphere, and the geosphere, right? Well, the hydrologic cycle, or as you may have learned it before, the water cycle, is the hydrosphere, okay? But it interacts with all the other spheres as well. For example, I drank a cup of water this morning. There's water in me. The hydrosphere, part of it, is taking place inside of me. I also take place in part of the hydrosphere every time I go swim in the ocean, right? The interaction between these spheres is constant. And the interactions and the unending processes that describe these interactions are called cycles. In the case of the hydrologic cycle, just basically, water evaporates from some body, let's say the ocean, okay? That goes into the sky, becomes its gaseous state. In the sky, it precipitates, usually because it cools off, coalesces around some particle or something like that. Makes raindrops. Those raindrops fall as precipitation, okay? The precipitation gathers, perhaps it gathers in a stream or in a lake, but eventually it either runs back off to the ocean or re-evaporates or transpirates from plants into the atmosphere. And that's your basic hydrologic cycle. It doesn't really mention, I mean, it does say infiltration here. If it soaks into the rock, it becomes part of the groundwater. That's what that's referring to. And that eventually does either come back out to surface water or I mean, it usually just comes back out where it stays in a reservoir, okay, which we will talk about in the next part. So, out of all the water on Earth, 97.2% of it is in the ocean, meaning it is not drinkable, salty. Actually, you can drink it. I don't recommend it, but you can drink it.
Really salty. Would not recommend getting in your eyes.
Yes, well, no, not in your eyes, no. Although I did, because I'm a Navy brat, I grew up in the Navy, right? So I spent every day of my life until I was 16 living next to the ocean. So I learned how to swim in the ocean when I was about 2.5. And so I actually got to a point where I was comfortable opening my eyes in the ocean to kind of like swim around.
Are your your eyes good? Actually,
No, but not because of that. Of the remaining 2.8%, 2.15% of it, that is fresh water, is in glaciers. That means 0.85% of all water on Earth is liquid fresh water. But of that 0.85, 0.62% is groundwater, meaning that 0.23% of all water on Earth is running or standing fresh water on the surface. Wow. Thank you, Owen Wilson. Okay, so that should give you a better idea of exactly how finite a resource fresh water really is. We need to protect that. There's not that much of it for us, and there's only more of us every year and less of that water. We need it. Water resource management is very, very important. Hydrogeologists are only going to get more important as time goes on. If you're looking for a career and you don't know what you want to do, I highly recommend hydrogeology. If you can get your bachelor's degree in 2 years from now, or maybe 3 years from now, get your master's degree in hydrogeology, a couple years after that, 3 or 4 years, let's say, then that puts you about, let's be generous with your time. Maybe you want a family at the same time. Maybe you want to work at the same time. You take your time. Let's say you get your master's degree 1 decade from now in hydrogeology. The world's going to be hurting for water, sources of fresh water, even more than we are now, right? Hydrogeologists will be worth their weight in gold. I tell this to every class every year. We're going to need them. If you think petroleum geologists get paid a lot of money to find oil right now, do you think people are more willing to pay through the nose for gas or for water? Which one do you need to survive when it comes right down to it? Right. So, all right. Let's talk about drainage basins. A drainage basin, okay, let me back up a little bit. Because we care so much about where our fresh water is, okay, where it comes from and where it's going, we separate the regions of land that it falls and flows through into what are called drainage basins. And these are usually designated by high point to high point, okay? Ridge to ridge, peak to peak, if we're talking mountains, okay? So, for example, I can say along this ridge, we'll call that one divide, and this ridge, we'll call that another divide. If a raindrop of water falls anywhere between these two ridges, then it is within this drainage basin. And it'll collect in one of these tributaries and eventually reach one of these rivers, okay? Until it comes to an outlet. But this is a drainage basin. And this over here is a drainage basin. And this over here is a drainage basin. And this is how we monitor and keep track of where water comes from and how much of it there is. Okay? Now, drainage basins, there are big ones, and then we break it down into even smaller ones. For example, this is the Mississippi River Drainage Basin. It covers most of North America. All water, any raindrop that falls within this green area ultimately comes out the Mississippi River in Louisiana. All of this water drains out that way. So it's the Mississippi River Drainage Basin. Let's break it up, okay? Now we're going to call it the Missouri River Basin, the Upper Mississippi, the Arkansas Red White, the Ohio River Basin, the Tennessee, and the Lower Mississippi. All of those are individual drainage basins, okay? And then we can break it up even more. One of the basins within the Missouri River Basin is the Yellowstone River Drainage Basin, okay? When I was working on the Keystone Pipeline, when I was doing paleontology work, I was in a little city about right here, which is too tiny to put on this map. Miles City was the nearest town. Baker, Montana. Tiny little town way out here. You'd have to go to Miles City if you wanted to go to a Walmart. Okay, but this is the Yellowstone River Drainage Basin. Okay. So we care a lot about our fresh water. And that's why we take so much time and trouble to monitor each one of these basins. Let's talk about the way that water moves. Okay? When you are in a river, how many of you have ever actually stepped into a river or a stream? I hope you have that experience someday. It is magical. Love it. Okay?
Especially when there's fishes.
Definitely, but I've been fishing.
You got pulled by the flow of the water. We're going to talk about that in just a second. Okay? I'll come back. I'm going to ask you more about that. When you enter into a stream, okay, you're going to notice a few things. There's going to be parts of it that seem to move fast and parts of it that seem to move slow. Okay? Jocelyn, where is the fastest part of that river? Sorry, can you say that louder?
It was towards the end of the lake, where it had like a little cliff that it would fall to,
Uh-huh.
and once you were getting closer to it, the water would speed up.
Mm-hmm.
So I was there, and I almost fell off there.
You almost fell off the waterfall? Oof, that could have been bad. But I'm talking about as you're going into the water, going further and further out into the river, did you feel it getting stronger, the pull? Interesting. So, the further you go out into your river, the stronger the current gets. Why?
Because there are no rocks in to hold it.
To hold it? There are no rocks to hold it. What do you mean? To slow it down? What is it that you're describing?
Is the water like pushing itself almost?
The water's not pushing itself. It is under the influence of gravity based. The faster it is, like typically the faster it's going, the steeper the slope.
Increase the momentum as it goes up.
What's decreasing the momentum?
Right, increase.
It's increasing its momentum?
If it's going down, right?
There's less friction.
I thought that's usually how flow works.
Yes, I mean, the steeper the slope, the faster it's going. But what I'm looking for is what these guys were just talking about.
The rocks are going like this. Like the river
The river's doing what further out in the middle?
is going down. It's going down.
What's that word? It's going down. It's getting deeper. That's the word you were looking for. Okay? The river is getting deeper the further you go out. That means what? That means two things. There is more water and less obstruction. Friction. There is less stuff. Less stream bank, less rocks on the bottom of the river interacting with water to soak up that energy. And so that water is just going to be, more of that water is going to be able to take that energy and just straight down the channel with it. Okay? So, as Jocelyn found out, the deeper you get out in the river, the more energy there is, the harder it is to resist it. I've had my own experiences with that. I empathize. Okay? And so you can end up in a dangerous situation, like almost going off a waterfall if you're not careful. This concept is true on straight rivers. Okay? The energy, the velocity is going to be fastest in the middle of your stream, of your river, when it's going straight. However, many rivers do not always go straight. Have you ever noticed that a lot of rivers seem to do this sort of windy, windy, serpentine sort of effect? Okay. Now, if my fastest velocity on a straightaway is in the middle, where do you suppose my fastest velocity on a curve is going to be? Yeah. In the curve? Yeah, well, where in the curve? Is it going to be on the outside of the curve or the inside of the curve?
So like if it was going that way, sideways.
The inside.
Why would it be on the inside of the curve?
Or like the outside, the outer outside.
Are you saying it's on the outside now?
Trying to imagine. Like it's going
Good.
like this, then it's going like a curve. So like the outside.
It'll be on the outside? Can you justify that? Anyone want to help him out? Justify why the fastest velocity for the stream going around a curve would be on the outside of the curve.
Because the water in the center has the momentum that's pushing it. I guess, like, I don't know how to.
Would it be kind of similar to how like a race car driver would drive around a?
The deeper is the outside.
Well, it's going to be deeper on the outside if that's where the water's fastest, right? If that's true. But that's a cause of the faster water, not why the water's faster.
And then, like, the water is taking away the obstacles when going the curve, like it's hitting it.
It's eroding the outside of the curve?
Yeah.
You're absolutely right. But again, you're describing what happens afterward, not why that happens. Okay? Let me help you out, though. All right? You're saying all the right stuff, just a little bit ahead. We're not to the effect yet. We're looking at the cause. Why would the water be fastest on the outside of the curve of our stream? Here's why. Everyone close your eyes. How many of you drive, actually? Before you close your eyes, how many of you drive? How many of you have been in a car while it's driving? You've never been in a car, Angel? How long do you walk to get here every morning?
He rides a bike.
He rides a bike. Okay, well, if you ride a bike, you'll be familiar with this as well, though not to the same extent. Okay, now close your eyes. You're in the car. If you're driving, sure, put your hands out on your steering wheel. If you're not, you're just kind of like playing on your phone in the passenger seat, whatever, okay? But, okay, you're going 35 miles an hour, and oh crap, that's my turn! Turning right. Barely even slowing down. Where does your body go?
To the side. Yeah.
Right, you're getting pulled left, aren't you? Wrong. Your original vector of movement was that way. All of a sudden, your car is going that way. Is your body a part of your car? No, it is a separate object being carried inside the vehicle. So your body's vector of movement is still the original direction. Your body isn't turning left. Your body is still trying to go forward. That is what that feeling is. Oh, snap. Okay? That's what's happened in your vehicle. And that's what's happening to the water in our stream. Okay? The vector of movement from that straightaway is still that direction. However, there's a whole bunch of rock obstructing it. It can't go that way. And so this wall of rock, which we call the cut bank right here, this is called the cut bank, okay, is diverting the water, it's forcing it to go a new direction. And now it has vector of movement that way. But because the water has to slam into that outside curve before it gets redirected, the fastest velocity is on the outside of our curve. That's why it's deeper, like what you were saying earlier. Okay? But that's that's an effect. Huh? You were, and that's why I pointed at you, like when you brought that up. Okay? Yeah. Faster on the outside. Okay. Race car drivers are familiar with this concept, right? Inside and outside both have different advantages, different strategies, okay, when it comes to race cars. But I'm not going to pretend to be an expert on that. But this is what happens with water. Now, on the outside of the curve, that's our cut bank. That's where material is being removed by that high velocity energy. That removed material ends up getting deposited on the inside of curves. We call this a point bar. So anything that got broken off of that cut bank makes its way downstream and gets deposited on that point bar. And so what happens is our streams kind of continually build out along these curves until they go so far. Eventually, these curves get built out so far that preservation of energy eventually kicks in, which is a natural process, right? And at some point, the curve gets so far that our river eventually just abandons that and snaps back towards the middle of the route because it costs less energy that way. Okay? So I'm going to show you a diagram that a geologist in Spain made. He's very talented at making these computer models, and it demonstrates how these Meandering streams, we call these. These meandering streams build out, and eventually they'll abandon a channel, and it's going to snap back. And it'll abandon a channel and snap back. And it'll abandon a channel and snap back. It's going to show you this over time. But also something you're going to notice is that as the stream is making this, it's going to be removing material. It's going to be those cut banks are going to be removing material. It's going to be deposited on point bars, but a lot of it eventually is going to get carried downstream. And so we're going to lose enough mass in this area that a river valley forms. And you're going to see how a river valley forms as a result of one of these meandering streams. Ready? Here we go. It's building out on the cut banks, depositing on point bars, and snapping back to preserve energy once those meanders deviate too far from the original course. And we are carving out a river valley.
Whoa.
Right?
Literally carving it out.
Yeah.
That's tempting.
There it is. That's how it works. Now, all that material that's getting removed, remember that process of carrying it away, we call that erosion, don't we? All that material that is getting eroded away is going to take on a couple forms, okay? You're going to have the material that's been dissolved. We call that dissolved load, right? That usually stays in your water until it makes it out to the ocean or whatever the outlet is. Then you've got your suspended load. Those are the particles that are small enough that the water has enough energy to carry them along, okay? Think clays and silts. And if the water is enough energy, sands even. Then your bed load. Bed load is anything that is so large that it gets pushed and pulled along the bottom of the body of water. So your gravel, your cobbles. And again, this all depends on the amount of energy your water has. Higher energy material, water is going to be able to carry larger particles as suspended load. Lower energy water is going to be able to carry smaller particles as suspended load and push those medium-sized particles like sand as bed load. And then again, whenever all that material gets dumped out, wherever it's going, we call that alluvium. And that's what makes those alluvial fans on land. Now I say on land because we have a different name for those if it's in a larger body of water. Any ideas what that might be? What would we call a large deposit of river-supplied sediment in, say, the Gulf of Mexico or the ocean? Where it empties out, the river's emptying out a bunch of sediment and it's dumping it all there. No, this is water-supplied energy, right? We call that a delta. You ever heard of that before? A river delta?
Yes.
Okay. Think the entire bottom half of Louisiana, right? That's basically delta built on delta, built on delta, built on delta as the Mississippi River builds itself out into the Gulf of Mexico. You can see that. Here's a delta, here's a delta, here's a delta, here's a delta. This is currently, this one down here, this is the delta that is currently being built out. And the Mississippi River just constantly is dumping all the sediment out here into the Gulf of Mexico that massive Mississippi River drainage basin is supplying to it, right? So a delta is when a river runs into a larger body of water, in this case the ocean, in the form of the Gulf of Mexico. This can also happen in lakes as well, okay? But it runs into this large body of water, and what happens when this running water slams into this larger mass of non-moving water? What happens to the energy in the river?
It decreases substantially.
It loses all that energy like that. And what happens when you lose the energy?
It dies.
Oh, it dies? It's so sad. No, what happens? What happens to my sediment? It falls out. With no energy in the water, it can't be held suspended. And so it falls out. And as it falls out, it extends our delta further and further out. That's how it works.
How is it made?
Okay, so a couple of other landforms that can form as a result of this. Alluvial fans, we already talked about. Same effect as a delta, except instead of hitting a larger body of water and losing its energy, this stream, this mountain stream, is reaching the bottom of the slope and losing all its energy and dumping all its stuff out, making this big pile of sediment, which we call an alluvial fan. Same concept as a delta, but on land instead. Okay? Then you have levees. A levee is formed on the side of your stream, on your stream bank or river bank, when it floods. So what is a flood? A flood is when the maximum capacity of your stream or river is overwhelmed by the volume of water that it's trying to hold, and it can't. Okay, and so it floods out. What does it take with it when it floods out? Sediment. So this flood water is taking a bunch of sediment out and dumping it along the sides of your stream or river every time it floods. And so every subsequent flood is building up this barrier of sediment until finally it reaches a point where this barrier of sediment, which we call a levee, built up on the sides of your river or stream, is large enough to contain the floods now. Can't flood out because the previous floods have built up the levee. We've learned from that. I'll show you how in just a little bit. All right. Some effects that can happen from flooding. Obviously, lots of disasters, lots of very unfortunate events have been caused by flooding. Some people here in town experienced that a few weeks ago. And even that is nothing compared to what some other people have had to face in the past, right? Flooding removes a lot of material and damages a lot of property. There are a couple of ways that you can make a flood. A regional flood typically happens when you have heavy rainfall, like what we had, okay? I would term that a regional flood because of the quantity of rainfall that we had for our area. It was atypical, and it can't go anywhere, and so it flooded through our communities. A flash flood, that typically will happen when you have some rainfall somewhere upstream and then that water washes to you, okay? And then an ice jam flood is when, say, winter's coming to an end. You have a whole bunch of ice that has jammed up a river, okay? Perhaps your river comes down to a narrow, like, sort of passageway in a valley at some point, and it got jammed with ice. Like when you get food, it's down at the bottom of your sink and your water can't drain out, right? Same concept. And so after a while, the water builds and it builds and it builds and it builds and it builds behind this dam of ice until finally it gets warm enough that that ice melts enough that the water can push its way through, and all of a sudden that water is released. Boom, bada boom. Everyone downstream is in trouble, okay? And then, of course, our own dams can fail. If you ever want to see an example of that, look at the Grand Teton Dam. Flooded several communities when the dam broke, allowing the entire reservoir behind it to escape through. Yeah, a lot of people call it the worst dam failure in American history. There's a joke there, but yeah. What did the fish say when it ran into the rock wall? Damn, yeah. Okay, now, I told you before how natural levees are made. We also make artificial levees, learning from those. Now, this is an artificial levee. These tend to work. They tend to work, except under the most extreme circumstances. New Orleans gets flooded all the time whenever there's a hurricane, normally because one or more levees fails to contain the river. Because these are not built through natural processes, over time, long periods of time, we make them ourselves, but we're not entirely familiar with the best ways to do it yet. We're still a learning process, and so sometimes levees will fail, communities get flooded. Still working on that. Okay, channelization. That's when you make sure that your streams and your rivers are deep enough to allow the passage of water. Okay, so if they get too shallow, then your rivers have to spread out to accommodate the amount of water. So if you make sure that your rivers and streams remain deep enough, the water can stay within those bounds. And so channelization is simply just making sure that that water has somewhere to be, making sure that they remain deep enough to accommodate that water. Any questions about running water? Okay, well let's talk about groundwater for a little bit and then try and squeeze some lab time in. Contrary to popular belief, there are no underground rivers. When I say groundwater, do not think that there is this river that we drill down into and tap our wells in. That's not how it works. Have you ever heard of dowsers before? Dowsers are people who believe that they can identify locations of underground water using copper rods. They are people who walk around with a pair of copper rods, and they'll touch the ground and they'll touch their rods. They'll say, nope, not here. Oh, I feel something. Yep, there's running water here. And they drill down. Of course there's going to be water there. There's groundwater everywhere. I don't know where this got started. Superstitious. I had a girl in my class one time whose father did that for a career, and I guess made a living off of it, convincing people that he could find them groundwater using dowsing rods. She was firmly convinced that it was true. No matter what I said to her about the fact that there are no underground rivers and copper could not find them even if there was, no matter what I said to her, she refused to believe it, which was fun. That was a fun class. Anyways, if there are no underground rivers, huh?
I was just laughing.
Oh, okay. If there are no underground rivers, what is groundwater? Groundwater is held within the pore spaces between the grains of sedimentary rock. Okay? First of all, before I explain that a little bit more, this is a picture of the inside of a cave. Any of you guys ever been to like Carlsbad or anything like that? Okay? It's fun. If you ever want to go, like, if you ever want to see what real caving is like, go on my YouTube channel, Heart Rock Geology, on YouTube. Okay? I have caving trip videos on there. I'm actually taking a group caving this Friday. I'm going to take them down to a cave in Iran. These formations are built, well, first of all, the space itself, the empty space. Is that a question? Oh, okay. This empty space, the cave itself, is caused by chemical weathering, usually inside of a body of limestone, leaving a void as the limestone has been dissolved by groundwater. These formations, stalactites and stalagmites, are what form as a result of the dissolved minerals in that groundwater reprecipitating and making those particular formations. Okay? So, groundwater is moving through and it causes some effects. Let's talk more about that pore space. The amount of water that a body of rock can hold is dictated by the porosity. How many pores are in my rock? Something like shale will have very few. Something like sandstone will usually have a lot. Okay? So this is porosity. What about permeability? Well, that's the other important one. Permeability is how connected those pores are. Why would that matter? Well, if they're not connected, can that fluid be transported? Can it move? No. And so this is very relevant for you petroleum engineers, okay? Porosity and permeability, very important. That'll dictate not only the kind of rock that you want to drill into, but also the type of machinery and infrastructure you set up to extract it. Okay, do I need to frack it? Will it flow out on its own? Do I need any sort of artificial lift system involved? Things like that to kind of help it along, okay? So what ideally we're looking for in both oil and water bearing rocks is high porosity with a reasonable amount of permeability. Why would we not want high permeability?
Water don't go through it.
Water would go through it, but what happens when the water's gone? All of a sudden, I've got a bunch of empty space. and it's going to crush, right? It's going to, you do that to a lot of rock, and all of a sudden, you're going to have a sinkhole on the surface, right? So highly permeable rocks with high porosity, you can extract from those. You just got to be careful about how you do it, right? Ideally, you're looking for a middle of the road sort of deal. Reasonable permeability and reasonable porosity, that's gold. Very little caution needed as far as those pore spaces being a problem later, okay? Also, that's a tangent I'm going to save for another day because we need to save some time. I need to make up some time. This one's going a little long. Okay, so hydrogeology is what I mentioned earlier, is the study of water, right? So specifically, water is a resource that we can extract from the ground. Normally, we'll drill our little straws down into what we call the main water table. Our water wells will go down into the main water table. Camera, stay with me here. Okay, so the water table is the line underground beneath which your rock or your soil is saturated. That is what all rivers and lakes are trying to get down to, that water table. Okay, they're gonna weather and erode their way down until they reach that point. Okay. However, if you're in a place like you built your house on a mountainside, getting down to the main water table may not be possible. That's a really long way to try and drill. So you look for what's called a perched water table. This is what happens when water that percolates its way down through the soil gets stuck on top of an impermeable layer of rock. We call that an aquitard, like in this case, clay, as an example. This aquitard, this water stuck on top of that, you drill down into that instead. Those are awesome. Love finding those. Whenever an aquitard interacts with the surface, it tends to come out in the form of a spring. This is a spring. It looks like water is just flowing out of the rock. It is, but through the pores in the rock. This looks like a river coming out of the rock. This is where the legend of underground rivers came from. If you were to go into that, and I have done this, if you were to go back there, climb through that water and kind of push your way through, you would see not a river, but this sort of cave, dead-end cave, and little holes in the rock where water is slowly trickling out. And all this water slowly trickling out of the rock is what is forming these waterfalls coming out, okay? 1,000 little pores through which water is slowly getting pushed out, combining to make each one of those little waterfalls, okay? A well is when you drill down into your water table. Now, normally, a water table, like in this sort of example, you're going to have to also attach some sort of pump. You need to get that water out somehow. It's not typically under enough pressure to come out on its own, unless there is one circumstance. With artesian wells, you don't need to do that. Artesian wells are awesome. In this case, an artesian well is what happens when you have some sediment layers that are at kind of an angle. Okay, there's a little bit of an angle here. And so I've got a clay layer and a clay layer, and between the two clay layers, a sandstone bed. Okay, that sand is going to absorb water very well. The clay is not. And so as my sand over here, where it's exposed to the surface, gets water soaking down into it, that sandstone's gradually going to fill up with water all the way down here, but it's going to be capped on both ends by clay. The water can't go anywhere. And so it is under pressure. It wants to get back up to the same surface as where it is getting filled with water over here. But it can't. Its water table is all the way up here. It wants to be there, but it can't be up there. And so what happens if I drill my little water well straw down in there? What's that water going to do? It's going to come up under its own pressure to try and get up to that elevation. Okay? That's an artesian aquifer. They are amazing. They are highly efficient. Love finding those. They don't need a pump. They come up under their own pressure. Now, we learned from this. We developed a way to use this concept that all of you are familiar with. You see it every day, but you never had any idea what it was for. Water towers. Water towers aren't just for storing water. They use the same concept as those artesian wells. You pump water up into your water tank, and this water tank full of water now is the source for water that goes to our homes and businesses. Because this is the source, wherever the water tank level is the artificial water table for any water that leaves that tank. So, because that is the water table, as the water leaves the tank and goes into your house and you turn on your sink or you turn on your shower, your water comes out under pressure because it wants to get up to that level, that elevation. That's how water towers work. We're making artificial water tables above our houses. If
That's cool.
Yeah, if all of this was being stored in a tank underground, you would need a pump to push it into your houses. But because we have it up here, no pump required. It comes out under its own pressure. Which is why, I don't know how many of you got that alert the other day saying, hey, we have low water levels in the tank. They were saying water may not work. You may not get water to your houses. It's because if there's no water in that tank, then it's not going to have any pressure to come out. Okay. Okay. I'm going to just breeze right through this. Water, groundwater specifically, I call it a non-renewable resource. Now, that is not technically true. Groundwater recharges. It comes back. Rain gets soaked into the soil, down into the rock. Groundwater is recharged. However, it is not recharged at the same rate that we consume it. Therefore, as far as you and I are concerned, it is non-renewable. It's the same thing with oil, by the way. Oil takes millions of years to form. We use it every day. There will eventually come a time, we're not near that now, but there will come a time when there isn't enough oil. We've consumed it, utilized it. And water is very similar. Groundwater is very similar. We use it at about twice the rate that it is recharged, meaning that there will come a time when the groundwater is so depleted that we cannot consider it a viable resource, or at least not a consistent one. So, what do we do? That's the question. But until then, we got to figure out a way to take care of it better. Okay? If our groundwater is used a lot, we can often end up with subsidence. The ground will collapse where that water used to be because where the space the water occupied gets kind of crushed under pressure, and that empty space gets filled with sediment, and so you end up with potholes and sinkholes at the surface. I'll show you some pictures of that in a minute. This is the High Plains Aquifer, okay, going all the way up from South Dakota down here to us. We use the High Plains Aquifer in our community, okay? Everywhere you see that's red, that aquifer, that water table has dropped more than 150 feet. The yellow is 25 to 50 feet. Even just the white, it has dropped, but less than 5 feet or so. All of these places that you see the red and the yellow, those are strong agriculture communities, ranchers, farmers. But as time goes on, these are growing. It's even bigger than this. This diagram is like, I think, 10 years old. So those spaces will have grown. Every summer, I help fix and install sprinkler systems around our community. It's kind of my summer job. I work for a landscaper. This summer, we had to redo a whole bunch of sprinkler systems and connect them to city water because almost every client that I did a job for, their well was dry. We're feeling it in our community. What's your option then? You can re-drill the well, enormously expensive if you're willing to do it. And then 20 years from now, you're going to have to do it again because the water table will have retreated deeper than that. Or let the city worry about the wells and you just get water from the city. That's what pretty much everyone decides to do. But more and more wells run dry every year, is my point. and it's only going to get worse. Keeping our groundwater from becoming contaminated is also a big thing. There are all sorts of stories that you'll hear. I used to live in a community where the local laundromat had been dumping water out in their backyard for decades instead of disposing of it safely. And over time, it made its way down into the groundwater, and kids in the community started getting sick. Those people went to prison, rightly so. They contaminated the entire groundwater system for their community by trying to save a few pennies. Okay,
What was it you just said where it was from?
Where's what?
What you were just talking about, the contamination?
That was when I was living in Hawaii. Yeah. So water, groundwater, finite resource, gotta take care of it. Okay.
I thought you were talking about that movie that I think it has Sandra Bullock in it.
I don't know. We can talk about that later. Okay, I'm trying to get through this real quick. When your groundwater gets heated up by volcanic activity, it turns to steam and comes out, and you have what's called a geyser. If you've ever been to Yellowstone, or if you've ever seen pictures, Old Faithful. That's what I'm talking about, okay? This is hydrothermal activity, okay? So geysers, hot springs, hydrothermally heated water. This is actually a tremendous resource for geothermal energy. I don't know if you guys are familiar with how power stations work. You don't just burn coal, make that energy, and it goes to your house. What happens is that you burn that coal, you use that nuclear reactor, whatever the case is, you make that energy, that heat. That heat is used to turn water or some other medium into steam or some other gas. That steam is used to turn a turbine. That turbine is connected to a magnet. Those magnets turning in tandem generate electricity, and that's what goes to our homes and communities. Okay? That's how a power station works. And so, what if you could skip the whole need for coal or any other energy resource? What if you just went straight to the steam? That's what Iceland does. I've been here to this power station in Iceland. Okay? It's fantastic. They are using geothermally heated groundwater, which is plentiful there because the entire island is volcanic. They just have to drill a well deep enough to get where the groundwater is hot enough to become steam. And then that steam comes up under lower pressure here at the surface, and they use that to turn a turbine. No coal needed, no fuel of any kind, just a well to bring the steam up and turn a turbine and generate electricity. They also use this superheated volcanic water to warm up some of the buildings in their capital city. It's really toasty. I love it. And then this is an example of some of the sinkholes I mentioned earlier. This is what can happen if you pull out so much water that that pore space that was once occupied by water kind of gets recompressed. And as it recompresses down below, space is made. And so at the top, on the surface, you get these sinkholes. And sometimes that will happen underneath someone's house, which is very unfortunate. The sheep care a whole lot less than the people that own that house. Any questions? Sorry it was a long one today. We spent more time discussing mass wasting than I usually do. But we had a good conversation. We had some good discussions. So I'm not sad about it. All right. Well, I'm going to end the lecture here.